So, hey everyone, and great evening or morning or wherever you are again. We are in another session. I think it's episode number 7 already of the Raspberry Pi Pico emulator live stream coding, whatever, hacking, yeah, whatever you call it. First of all, hi Andreas from the chat. Good to see you here. And please let me know in the chat if the audio and video are fine, the usual stuff. Meanwhile, I will start with sharing my screen. So I think this is where we left off last week, looking in the hello UART and how it interacts with the table lookup of the boot ROM or something like that. This is our code. And before, thanks Andreas for the feedback. Before we go deep into the code again, I will just tell you a fun fact. So I spent the weekend looking into the PIO section of the datasheet just to get a feeling how big this is, and at some point we'll add it to the emulator, so to get some understanding of what a PIO is. And they have a section of examples there, so you can use. So the PIO is basically a sort of micro machine language that lets you actually probably explains it better here, or maybe no. Yeah, it's a programmable input-output block that basically let you implement your own protocols, so it can interact with the GPIO, and there are like state machines that you can code. And then they have all of the description of the PIO, and finally there is a bunch of examples, and they show you like this code to create SPI, to drive LEDs, to create USART, UART, and I2C, PWM. And they are like all like, this is the PIO assembly code. And they are all very useful and down to earth. And then there is this addition. Although it's not designed for computation, PIO is quite likely Turing complete, and it's conjectures, I don't know, that it could run Doom. It means that somebody believes it could run Doom, given a sufficiently high clock speed. Now, they have like an example that adds 2 numbers, but note this: a full 32-bit addition takes only around 1 minute at 125 megahertz. That's the speed of the Pi Pico. So yeah, they sure have some kind of weird sense of humor, including this demo. And if you look at the source code, you can probably realize why. They have like a loop that decrements from one number and increments the other. So adding a number is like O of n, big O of n. That's a very slow way to add numbers, but it's possible. Yeah, anyway, that caught my attention while I was looking at the PIO, this funny addition, useless example. Another thing before we start. So last week somebody left a comment on the YouTube video. I think it was Paul who left a comment, and he said that there was another live stream from Adafruit where Scott, that's their engineer who was working on CircuitPython, was also looking into the boot stage 2. He was trying to implement something for CircuitPython, so he tried to look into that and understand why their the flash chips that they used in their prototypes didn't work with the boot stage 2. And the funny thing is that they also got confused by the same thing that we had, like this. I think it was that there is like the generic boot stage 2, but then that's yeah, that's not the default one. The default one was, I think, this one. So they also got confused by the very same thing as we did. Anyway, it was fun to watch him try to write his own boot stage 2 in C, and then it didn't work, and he tried to debug it, and that didn't work as well. Made me feel a little bit better about things that go wrong in this live stream. So anyway, with all that fun stories, let's get started. So today our goal is to understand what we did last time. So let's first of all run the code and see where we are at. So I think we were trying to run USART, and it seems like that there are like some missing instructions, and we probably left ourselves a message. Yeah, we need to add a few more instruction. And there was like this DMB, which is, I think somebody mentioned last week, data memory barrier. And this probably, if I understand this right, this just means that the CPU should flush the data cache or something like that after this instruction. Nothing to worry about right now. So we can probably maybe include this instruction so we don't get a warning, but we don't need to spend too much time worrying on that. And then there are like all of those instructions. And just out of curiosity, it seems like when I npm start, it seems like it gets into somewhere, like it gets into some place. It doesn't seem to be inside a loop or something like that. So let's just skip those instructions for a moment and see what happens if I just go to run Blink and tell it to run 10,000 instructions. So just go with it and see what happens. So yeah, so now we see we are actually trapped in a loop somewhere else. So let's see where we are at right now. What is this loop? Where have we landed? So we can close this window for now and go to the hello UART and take a look here. So where are we? Panic? Are we inside a panic? Oh my god, we got into panic. So yeah, so maybe not implementing the instructions wasn't so good idea after all. If we got into this panic, but by the way, the panic should have probably, it called printf and stuff, so it should have probably printed something to serial, but we may have not have initialized serial at this point. Oh, and I guess that's missing instruction is this one, breakpoint. So obviously we don't have GDB or something like that right now, so there is no use in implementing breakpoints in the simulator. So what I'm going to do, I'm going to just dump this into output.txt to see who called panic and try to realize if it has anything to do with the missing instructions or we just got into panic for some unknown reason. Let's find the first occurrence of this. So here we go. I think this one. So this is the first instruction that we have before this panic, and it's probably this it's probably this implementation of rep puts, because where are we? Yep, because that's called from panic. But actually I would like to see who called panic. So let's go. So that's where panic is. Let's look where the first, yeah. So we got to panic here after we read something from some memory address. Okay, interesting. So let's see what sent us to panic. Hard assertion failure. Oh, that sounds really bad. And how did we get into hard assertion failure? From here. What's this? Oh, IRQ set exclusive handler. All right. So yeah, it read this value here, and let's look at the source code for that. That might be a bit more useful. This is calling the function. Where do we define it? Probably IRQ sounds. Oh, okay. I guess it's Okay, I guess it expects to find something and it doesn't find it, and then it panics. All right, so yeah, we have a missing instruction here. Just a few instructions before this panic. So let's see what's there. LDR. Yeah, I think we got that one in the list we need to do. LDR. Yep. No, we actually did it. We have it with LDRB and not LDR with 3 registers. But anyway, it seems like we need. We are going to suffer if we don't implement them, because they are still used. So let's start by implementing those missing instructions, and maybe we'll get lucky. I guess not, because I guess we need to realize what this function is doing and what is this IRQ get vtable handler. It should be yeah, so if I understand correctly from this function, it reads the vector table, I guess, and then it looks if the current slot is empty, and if it's empty, then or it's equal to the handler that is passed, then everything is okay. But we probably haven't implemented that. We got this read from this address. Why are we reading from the flash though? Not sure. It seems to get vtable handler. Not sure. Anyway, it obviously is not going to read from the right place, because it has this instruction that we haven't implemented. So and I think that's how it reads from that's probably the implementation of this IRQ get vtable handler. So without this instruction, we are not going to get anywhere. Anyhow, we are reading from the wrong location probably. So let's do that. Let's start with this one. LDR and 3 registers. How do we I'm already waiting for like this point in time where we just have all the instructions we need and we don't need to go back and implementing them. But I feel like we are pretty close to that. So which one do we need? LDR register, right? And let's also do LDRB register, because we concluded last time that we need that. So why not? All right, LDR register, so it gets 3 registers, and then I guess so reading from the registers, index is true, add is true, write back is false. I guess that's what W back, and then the usual thing, no shifting, and then we are taking RM and RN. It is true, right? RN plus offset. And then the address is if index, and index is true, then offset address. So offset address is just RN plus offset, which is RM. So basically adding those two, looking at the values of those 2 registers, looking at the memory address and reading it into that register. Shouldn't be too hard. Let's do that. So as usual, we'll start with a test case for the assembler. So assembler spec and assembler, and that's opcode LDR. Don't have it, LDR. Okay, function opcode LDR, and let's also create a test case. So we can close this for now. All right, it should correctly encode and what was that? This instruction, right? And we expect opcode LDR with those friends R3, R3, R4 to equal this magic value. All right, opcode LDR, and let's see. So we said it gets RT, RN, RM. Oh, we can copy those from here. And RM number, and the encoding is just this, and then M and T. So return this. And why is the test runner not running? I want to see green. I want to see them all green. So this is shifted by 9. And then we have, too bad we don't have something to copy paste, but it will take a moment to create this. So shifted by 6. No, we said it's M and T, not TMN. So M and then N and then T. This is by 3, and this is without a shift, and formatting, and green. Yes, it passes. So we have the encoder for that. It's actually, let's call it LDRH, because there is also the LDR immediate. So that would be LDRH, and then opcode LDRH here. Cool. And then let's do the same for the LDRB. So we know that we wanted to implement the register version of it. And actually, let's do all of them. LDRH, they are so similar, so why not? So let's do LDRH reg and LDRB reg. So no, yeah, we just need this for the LDRH. I mean, we know we'll need it at some point, so why not do it now when we are already doing a bunch of similar instructions. So, and LDRB reg is just LDRB register. There is also LDRSB. We are not going to finish with that today. All right, LDRB register. So that's T, that one. We're probably missing a 0 here, I guess. Or wait, no. That should be shifted by 9, not by, oh, yep. So this one should be similar to this one, but just a different encoding. So now it makes more sense to me. So this one, and then LDRH. Oh, and the parameters should also be the same. I should have just copied this one into the 2 other ones. So same parameters. And then for the LDRH, that was, no, the LDRH register. It was this. Cool. And then there was also LDRSH, right, with register, which is quite similar. So let's do it as well. LDRSH. Isn't there an LDRS with register? Only, wasn't there an LDRS? Why do you have an LDRS? There is SB and SH. So which one is? There is no LDRS. So why do we have here an LDRS? Oh, that's an LSRS. Too many similar instructions. Anyway, so we have LDRBH register and LDRSH register. So BH is, oh, that's not BH, that's SB. LDRSB, yep. LDRSB is this. and we will shortly create quick test cases just to see that we got everything right. And LDRSH is this. It's like they're signed versions of the other LDRs. All right. Is there like for those? Yeah, there is also. Oh, those one don't have an immediate version, so it's always registers. So we don't need the regis if there is only one version. All right, so let's quickly find and create test cases for those ones. So we have LDRB. Let's find some random LDRB with registers. Yeah, I think that one was good. Yep. As our candidate, where is LDRB? So we have LDRB with this happiness. And then that's the expected encoding. And then we say we want LDRB with registers with R2, R5, and R4 to equal this. Green, excellent. Now let's look for LDRH with registers. Nobody is using LDRH with registers. Let's do it like that. That would be faster. Ooh, I think we found an opcode that exists, but nobody uses it. Oh, I found one. Yes. Great. So that's the LDRB, and then we have this LDRH. So, and that's the instruction R4, and that's the opcode, and that's LDRH reg with R4, R0, and R1, and let's import it, and it's green. Perfect. So we only need to test this one and that one. Let's see if there is an LDRSB somewhere in this code. Better be one. Yep. So LDRSB should be a space. I don't like tabs in the test name. So opcode LDRSB with R3, R2, and R3 should equal this number, green, and LDRSH. Ooh, nobody is using LDRSH. Or somewhere somebody is. So luckily we have one usage of that instruction. So that's not a lot, but it's still good enough for creating a test case. So LDRSH, and this should equal this. So that's LDRSH with R5, R3, R5, and it passes. Okay, so we have a bunch of new LDR instructions ready to like we can assemble them, and now we can create the actual test cases for all those 5 new instructions, 5 new LDRs. So we have let's see, let's say we want to test LDR, so R4, R3, that would be, let's say, R5 plus R6. So let's say R3 is that would be opcode LDR reg with R3, R5, R6. And then we have some value in R5, let's say, yeah, this whatever value. And then we have, what did I just do? This value in R6, which is just the offset. Let's say it's 8. I guess it must be word aligned or something like that. And then SRAM at 8. So this is the address of SRAM 8 would just equal like, let's say 1, whatever. And this one will, the next byte will equal 42. And then after that, we expect R3 to have this value. So 4201, that's like the higher byte and the lower byte. Let's actually add another one just to make sure it loads at least. You know what? Let's add all of them. So that would be 24 or 55, just to make it easier to understand where these numbers come from. Cool. So maybe let's do this one, 11. Cool. All right, so we have the test case for LDR. I hope I got it correctly. Let's double check in the LDR register. Is there like, yeah, I guess this means that this is 4-byte aligned. Not sure about the syntax. Maybe we should take care of that. Loads a word, offset addressing. Well, let's take a look at that. Alignment sounds good. Yeah, I guess if it's not aligned, then we are supposed to generate a fault, but let's not worry about that at the moment. The code shouldn't do it if it generates a fault for the most part, unless they have like some code that protects from running in emulators, and then we'll have to emulate that. Anyway, let's do the LDRB version now. So LDRB should be, we can do like the same setup, so that would be LDRB reg, and we expect this to load, you know, just 1 byte because it's LDRB, and then LDRH, so LDRH should load just 2 bytes, so 4211. And we also had, I think, LDRSH. Have we implemented LDRSH? We did. Interesting. All right, less work for us now. So opcode LDRSH. Let's just use the new, function we created instead of this. So we only need to add a test case for LDRSB. Wait a moment. So we have LDRB. I guess it would be, or actually, let's take the LDRSH opcode test and adapt it to a single byte. That shouldn't be too hard. LDRSB from the same registers, and then we want the first byte to be negative. Let's say it's 85. So this should be 8, a lot of zeros, and 5. How many zeros have we got there? I think that's about the right number. So just sign extending the result. So this is the negative bit should keep being the MSB like it's here. And there we go. We have all the test cases for the new instructions, and I think implementing them will be pretty quick. So let's see, we have LDR immediate, LD, and let's do LDR register. LDR register. So for LDR register, that would be, where is LDR register? Yep, we want 9 bits to be this. So 9 bits. And then I think we can copy the decoding from LDRSH because it uses the same registers as we have seen above. And then these registers RM. I guess this is also, yep, it's the same in LDRSH. And then I think that's it. Yeah, it works. It's green. Yeah, perfect. So we have the test case for the LDRSH. That one. Okay, it's not green. Interesting. Why? Expected this. Oh, that's the LDRH. We were talking about the plain LDR with registers. Yes, it's green. Great. The next one is the LDRB. So let's just copy this and do it with LDRB. So what's the opcode for the LDRB? Register. We need to take this and then why doesn't, oh yeah, and then we just read uint 8, I guess. Yeah, and it passes. So we have all like those primitives of reading uint 32 or 8 ready. So it's a breeze to implement those instructions. It takes like seconds. All right, and then there we have LDRH register, and that's where is LDRH. That's the opcode for the LDRH register. All right. And then we need to read uint 16 and it passes. Perfect. And finally, we have also LDRSB, which will be very similar to LDRSH, just doing 1 byte instead of 2 bytes, half a word. So that's LDRB, goodbye many spaces, and we need to sign extend 8, reading uint 8, and it doesn't pass. Why doesn't it pass? It doesn't go into here. Oh yeah, because we use the wrong opcode here in the test. So it's the test fault, and now this is green and this is green, and we got a bunch of new LDR instructions. Let's see if this changes the panic, if we still get into panic or we got somewhere else. Yeah, I think we are still at the panic. It seems like we still got to the panic, even though we implemented a bunch of those instructions. The good news is that we are almost out of non-implemented instructions on the way. There are still a bunch of them. Let's see what's here, for instance. What's this one? Just out of curiosity. Oh, that's the boot ROM, somewhere in the boot ROM. I think we had a disassembly of the boot ROM though. We had, but we lost it. Do we have that file with the hexa open, or do we need to do that again? Anyway, never mind. I guess it's not like just one instruction somewhere. We'll probably get to it. Yep. What else? So we have this one, which is the break. Yeah, I think most of them are covered. What's there? What are we missing here? LSLS. Yeah, I think we had that in the log for what we need to do. Yes, let's do that then. LSLS. And we already did this one, so let's do these missing ones as well. We worked so hard last time to figure out we needed them probably, so let's do them. Shouldn't take too long. Where is LSLS? LSLS register. There is immediate and register, and this one is with register. We probably have the immediate. I don't know. Let's do the encoding first. So assembler LSLS. No, we don't have LSLS, or at least we don't have the opcode for it. So we have LSLS reg, right? And it takes RDN and RM, or they call it here, yeah, RDN and RM. And then it returns, or maybe we should do the test first. So let's do the test first. LSLR. Right, so this thing should equal LSRH with R5 and R0 should equal that value, right? And LSLS, yep. Now it should be, let us import it, but for some reason it doesn't. So let's just add it here manually. And test case doesn't pass because we need to encode it. So we have this thing shifted by 6, right? Go away spaces, and then we have RM. That's 3 bits, right? Yep. Shifted by 3, and what did I do? Don't need that one, and we have RM, right? No, that's RDN now. The second one. Yep, RDN. Cool. All right, it passes. Cool. Now let's implement LSLS. So let's start with this test case. Oh, we have the LSLS, we just don't have the encoder for that. So it should be a breeze to implement a version with just 2 registers. So in this case, it was code LSLS reg. So we had our, what did I do here? Yeah, R5 with R0, R5 with R0. Now I have to see what this does. Probably shift left shift. Yeah, it sounds so. I guess it shifts the value, register value left by a variable number, shifting in zeros, and write the result to the destination is read from the bottom byte of a register. All right, so we probably, yeah, we are taking the bottom byte. That's something cool. Now that we know that, we can say we want to shift this, and then we can like put here some garbage, like, but we just want the bottom byte, which is like 02. So now our test case will actually test this behavior, and then we expect the result to be like the input, but shifted by 2 bytes. And yeah, it also updates the flags as usual. I think carry is true only. Yep. Anyway, we can just probably copy the implementation of 2040 LSLS of that one. So that's the one with the immediate, and then just, change the inputs. So LSLS register, and then if the opcode shifted by 6 is equal this whatever, then we have LSLS register, and let's decode it. So RM is just yeah, and then there is RDN, and instead of like shifting it by IMM5, is there like a reason? Yeah, I guess we can const input 2 or shift count. That would make more sense. It's just register RDN, but we need to take, so if we do this, the test should fail. It's a good idea to test the test. I have no idea why we're doing this. I mean, shifting by 0 shouldn't change the number, so that should be okay. And then RDN gets the result, and carry is, I guess, shift count instead. So obviously this failed because shift count didn't take the bottom byte. Yeah, actually, can we see it? There is like, no. But if we just take the bottom byte, then we expect the test to pass, but it doesn't. Let's see why. Yep, it expected this, got this. We shifted a lot. Let's see, console log shift count. Let's also focus. Yeah, it shifted by 3, even though I'm pretty certain the lowest byte here was 2. Oh, R0. How comes? Oh, I guess we swapped the registers somehow. Oh, how did that happen? So yeah, RDN is like the input, I guess, and RM is how much we are shifting, right? RM is how much we are shifting, yeah. So the test helped us to find one issue, and then it still doesn't pass. Let's see why. So now the shift count is what we expect it to be, it's 2. But there is unhappy test, received 0. Oh, wait a moment. We are shifting right, not left. That's the reason. And now we almost passed. Why did we have, yeah, I think we should copy the condition from here. We probably copied it from, wait a second, from, yeah, I think I messed something up. I think I copied this into this and then edited LSLR. So luckily we have Git to save the day. Where is this original LSLR? Yeah, let's restore LSLR first of all. So this is this one and this one, are they equal? Yep, they are the same. So we can remove the duplicate, and then let's add the LSLR back from the Git history. And now let's see what happened with this one. So the condition here should obviously be the same as LSL and not the one we took from here. And then that also explained why we had the wrong operator here. Instead of IMM5, it should be shift count, and now we are green. So thank you, tests, for covering all the issues, for discovering all the issues that I had in the implementation. I hope it's all of them. And now everything is green. This is great, and we got one more instruction ready. Let's start this thing and see. We are still in panic, and I guess the reason for that is that we are reading from somewhere and not finding the value that we are expecting to find. There are a few more, like why are there, like, why is it running instructions from the SRAM? That's interesting. Yep, no idea. Anyway, and it happens pretty soon before this panic. Maybe have something to do with that. We'll have to look into that shortly. But before we do that, yeah, we have a few more instructions we haven't implemented, like, oh, that's inside panic. So I don't want to implement stuff inside panic. We don't want to get into panic. And what's that one? It's at R1 SP4. I think we had that one. No, we had add R1 IP, which is still missing, and there is still this one which we haven't done. So let's do that one first. We may need to save something somewhere. The code tries to save something somewhere into the memory, but we haven't implemented that STRB instruction, or so we think. Let's see. We have STR register immediate, but and I think, oh, that's STRB. Yep. So we only have the STR. We don't have like STRB and probably there is STRH as well. Let's see. Yep. Ooh, there are like a few of them. So yeah, let's do that's STRB mediate. Let's do that. So just for the sake of completeness, and because we said we will do it last week, we need to do what we say we will. All right, so let's do the STRB, and that's STRB immediate. So do we have like something good to copy from? Yeah, I think this one would be a good start. So opcode STRB, and STRB is just like this thing, and we have like IMM5, RN, and RT, and here it's called RD, but I guess it's the same. So RT, RN, IMM5, and then it's IMM5 shifted by 6, RM, and RT, right? Yeah, it's fun to copy paste. And let's, I forgot creating the test cases first. So that was STRB. Let's create a test case for STRB. Assembler spec ts, str, we don't have str yet. Whatever, let's just copy this one. STRB, that was this, so STRB. And this operand, so opcode STRB with R3, R2, 0, we want it to equal this value. Right, and it passes because we did it correctly, right? Let's also do STRH because we are already on it. So this is like STRH with re-register, so expect, I should copy the test case. So STRH reg, and that was like R1, R3, R2. Was STRB, STRH, R1, R3, R2. So this one, R1, R3, and R2 should equal this. And now let's implement the encoding. So in this case, it's probably similar to the LDRB reg or LDRH, doesn't really matter. So STRH reg. And then just find encoding STRH register, so this, and then MNT, cool. So just change the opcode, the prefix, and we are import it. It's not happy because R3 and R2 we didn't copy paste correctly, and it's still not happy. All right, maybe we didn't copy the opcode, have we? R1 3 2 1 3 2 1 3 2. Right. Why is it not equal? Ooh, that's a big number. Right, it seems like something is here is off, but what's that? I think that's the same big number here. Yep. How did we get such a big number? This one is big. Huh? Oh, right. It should have been binary, not hexadecimal. All right. Thank you, test. Good catch. All right. Yep. That's what happens when you implement too many instructions in a row. You get tired. Anyway, let's do now the other STRH with, yep, that one. We didn't immediate. So that would be STRH with R1, R3, and 4, and it should encode to this. And then that's STRH without register with an immediate, and it should probably be very similar to just STRH. You can't import it. Yeah, sometimes these auto imports they don't really work very well here for some reason, so we have to manually import them when we define a new function. That's annoying. All right, so R1, R3, R4. Okay, so now we just need to do the STRH. Go to the datasheet, STRH immediate 1, and all of the other ones are 0. So 2, and it's not green. Why isn't it green? That's STRH immediate. 1 and 0s, IMM, RN, RT seems to be nice. Oh, 0 extend. Ooh, yep. So we need to shift this IMM by 1, and now it will probably be happy. Yep. So when we are like storing a byte, the address doesn't have to be aligned, but when we are storing this 2 bytes, like half word, then the address has to be aligned. So there is no point in having like the least significant bit of IMM5 or the address set. So we always add 0 to the IMM5. So thanks to the test, we quickly spotted that thing. All right, and then I think just for the sake of completion, let's do the other STRB as well, which happens to happen. Oh, that was, we already have that one. We need the STRB with 3 registers. So let's do like we did before, just like search and find. Ooh, that's one with the opcode. So no, that's not 3 registers. Whereas it's not very common to use it with. Very uncommon to use it with registers, but I'm sure somebody is doing that. Oh, here we go. There we go. So that's STRB with 3 registers. So STRB with this R2, R3, R5 should equal this 5553. Okay, and now we can just copy from STRH. Should be probably very similar. Oh no, that was STRH reg. STRB reg. Probably just the prefix is different. STRB. Oh, thank you, Steve. And are you still without? Oh, okay. Thanks for the feedback about the 0x. I just saw it, so thanks. You probably spotted it before I did. And also, no worries about the audio. I'm happy that you give me this feedback in the chat, because if you lose audio, I definitely want to know. And by the way, hi, good to see that you are here, like every week. I really appreciate that. All right, we were looking for the encoding for STRB. Where is that STRB register? STRB register. and out of that happiness, and then just import this one. And again, it doesn't want to import, so we need to do it manually. And this is green, so the test has passed. Yep. So now we have we can encode all the STRBs. Let's create the test cases for the STRBs. No, I want the spec file. STRB, or all the STRs, not all of them are B. We had some STR, yep. Actually, I think we can also do the STR register, which we don't have right now. So let's do that as well. And just for the sake of completeness, let's also do like the opcode of STR immediate. We have like the test case, we just don't have the opcode. So let's do the opcode and be happy. So this is like what we use in the test case. We'll use it for the opcode. So opcode STR. Yep. So we want to encode this into this R6, R4, and 20, and then STR, and that's just need to implement this encoding. So this is STR, so we have this prefix. All right, and I already fell for this once. It's probably not going to import, huh? All right, so opcode STR. Yep, I already fell for this one, so I know immediately that the reason it doesn't pass is because we are going to add 2 zeros here to the IMM. So let's fix that. So just shift it by 2, and now it passes. Now with this new opcode STR, I can make my tests a bit prettier. So R6, R4, and 20 should pass, yep. And let's do also the strreg for the sake of completion. Let's find a sample. STR. Not too many STRs, or it's probably a tab after that, and that's why it doesn't find it. Tab character. What was that? We'll just copy paste the whatever comes. Yep, tab character. And one with 3 registers. There must be one with 3 registers. Oh, they don't like those register variations. They don't use them a lot or almost at all. But I think, yep, I spotted one. Yep. So let's take this one as a test case. And this time it's strreg, and we expect this one. Don't want any tabs here. Got rid of all the tabs at once. Yep. So R4, oh, that one. So that should be R2, R1, and R4 should equal this. Right, and I guess it's very similar to the STRB reg, just a different prefix. So what's the prefix for STR register? That's the prefix. All right, so this is not green because we need to import, and auto import still doesn't find a new function. And now it's green, which is nice. Okay, so we have all the opcodes that we need. We can close the assembler for now, and let's write the test cases. So we already have one with this. Let's just adapt it to the new situation. So instead of R4 and 20. Let's do R4 and R5 and put 20 in R5 and opcode strreg. Now it auto imports, so R4 and R5, and it should basically be the same as before, just reading this address from a register. So now we have to do the same for STRH and STRB. Let's start with the STRB and with little modification. So in this case, we are going to do STRB, and then let's put some value in the RAM. So just, to see that it stores 1 byte. So rp2040.sramview dot so it's 20 hexa plus 20. Not sure why I mixed like hexa and not hexa. Let's fix that. Let's do it like 10 hexa, or maybe even 5 hexa. It's byte, so we can do like 1 hexa. No, access it unaligned. So all right. So what did I do here? Yep. So I want to sramview.set uint 32. So I want to set, let's say, to F5, F4, F3, F2, and that would be at 20 hexa and little Indian. We fell for that too many times already. And now after executing this, I can keep it like let's F055 in R6. So that's what we are going to store into this memory address, right? And then we expect the result to equal. So it should keep the same one, but it should change. So we change this byte. So it should be the second byte should be 55. So that's a pretty complex test case, and assert that the second byte at 01 change to, just to make it clear what's going on here, because it's a pretty complex test case. And then I guess I'm going to remove all the tabs here as well. Right, and then I guess this is STRB, and then we want to do the same with another register. So just copy this test case, and then let's put this value in R5, 2040 registers. R5 gets 1, and then here is R5, and other than that the test should be the same. And now let's do STRH. So for STRH we want to store this whole new word in this. Let's do it 2, because it has to be aligned, and that's STRH. And this is STRB reg actually. That's the standard one. That's the one with the register. So strreg should store this. So basically after the change, let's do it 66 for 55. So after the change, assert that third, fourth byte at 22, change to 60, and then actually that should be reading from the original address 20 hexa. We want to check all the bytes. Yep, so that should be 66, and then F3, F2. All right, so we have the test case for STRH, and now let's do another one for the one with the register. Let's make it more interesting. Let's do it R1. and then we put this value inside R1, 2, and this is STRH reg and R1, and I think we are good to go. Or if I forgot something, let me know in the chat, but I think it should be pretty similar. And now the very last thing is just to implement those. So let's start with str, just copy paste, and let's take the encoding from LDR register because it's the decoding. So there is str immediate, str register, so decoding, and then the address is just, we could copy that as well. And add, let's call it address. So I think this should do the trick. We should just find the prefix. So str register, that's the prefix. And the shift should be changed as well. No, I'm not going to write there X again and spend too much time on that. And I think that should work. Yes, that's green. Perfect. Okay, on to the next one. What else? What do we have here? So we had STRB, which is a bit. Let's start with the immediate. Again, we have probably write uint 8, so it should be easy. STRB immediate should do. Let's see. This is the opcode, the prefix of the opcode. So this one, and then the decoding should be the same, the address, but we should only write. Oh, one thing we should do, we should not shift the IMM5. We already know that this is a big difference between STR or LDR, the B and the not V variations. And we don't have write uint 8. That's too bad. We do have write uint 32. So let's see. So writing uint 8. There are a few ways to do it. I guess the best way to do it would just be so write. We'll also need the 16. So address, value, number. So I guess the best way to do it is just to read the value, change the specific byte. So read the uint 32 at address and yeah, like we did before. Where were we? Yeah, just read the whole uint 32. Let's call it original value, and then const new value is okay. So we need to find the offset, which is just the lowest. Yeah, the lowest 2 bits of the address, the offset of this specific byte inside the word, and then new value is so we take the original value and shift it, and we need to mask out the specific byte we are replacing. So that would be FF shift left by. I guess there is a better way to do it, an easier one. Yeah, I mean, we can do something more readable like this. Or maybe yeah, so we can probably, this is like this one is easy because we can call setuint. If we are just writing into the RAM, we can call the write setuint. If we are writing into the SAO, then we probably, this will probably be replaced by this write hook, but I guess we need to either make the write hooks support arbitrary writes, or we can sort of always simulate like we are doing here, writing 32-bit value. I think that would be easier if the write hooks always assume the writes are like 30-bit values, but I'm not sure. It might bite us in the future if there are like specific registers where you can write just 1 byte and it has a meaning when you write that byte. I know that in AVR it exists, but hey Nekati, by the way, good to see you in the chat. So if any of you is aware of a situation if in this Raspberry Pi where writing a single byte versus writing the whole, updating a byte in the whole D word matters, let me know. Otherwise, we can just like do something like that. Const, let's call it new value bytes is a new uint32 array with just the original value, and then new value bytes by offset equals value. So just change the specific byte in this array, and then oh, that's uint. Oh, we need to, we can use a data view here. So new data view, creating a lot of temporary objects, but we can optimize that later if we need. The purpose is to get it to work. So we're creating a data view and then set, why isn't, oh, data, not date view. So yeah, so set uint8 at offset to value, and then we can just call it new value, and then we can just call write uint32 address and new value by index 0. So basically that's, so I removed the offset, const offset equals address and just the lowest bits. Cool, and then we can use the same trick. Interesting to see that this is green already, which means that we implemented it correctly, probably. STRB probably, yeah, it passed. Cool. The first one with so yeah, so we didn't implement it totally wrong. I'm not sure if we implemented it totally correct, but it seems to be good. And now with write uint16, we just do the same, but the address, yeah, it's still like a bait address. It has to be aligned. So ideally we should throw, let's just document this. We assume that address is 16-bit aligned. Ideally, we should throw an exception or generate a fault. If not, just so one day when we get bitten by it, we'll know that we knew what we should do, but we haven't done it because we were lazy or because we just wanted to get it to work. Anyway, so the only difference is that we are now going to call set uint16 and little Indian. And that should set the specific 2 bytes, the specific word in this address. All right, so that was, so we had STRB immediate. Let's do STRB register, which is similar to STR register, just the opcode is different. So STRB register, this is like the prefix 0b, and then removing this and just write uint8 and it should be green, or it's not green. Why isn't it green? What have I missed? Right. should be very similar to this test case, like, oh, wait a second. This is strange. Ooh. Yep. All right. So I had a bug in this test. I tested the value in the wrong address. We wrote this value here. We expect it to stay here, but apparently it seems like, yep. I wrote the modified value back to the wrong address. I should have maybe const base address. Yep, I should have written it to the masked address, like to the aligned, maybe aligned address is better name, and then I should write it back here, and should do the same with the right uint16. And luckily, having multiple tests, one had a bug, one didn't, caught that issue with right uint8. Otherwise, we would have to hunt for it while trying to figure out why the code that we are emulating doesn't do what it's supposed to do. So here, let's do it the same, aligned address, and this should also be fine. And now let's just do STRH. Do those, both of those at once. So instead of uint8, that would be uint16. And we just have to copy the opcode and hope we didn't miss anything. So STRH immediate, that's the first one. Just one and a bunch of zeros. And it's not green. Why isn't it green? Oh, yep. I know. We had to do this shift with the immediate. I know. Where did we do it? In STR. We did it here, so let's do it here as well. All right, and shift 1, and it's green. Perfect. And then the register one, we just need to change the prefix, or so I hope. STR register. Let's see. Prefix, where are you, prefix? And there we go, all green and good. All right, so we got all those instructions that we wanted except for this one. So let's do this one. We have add. I'm pretty sure we did add at some point, but probably not with 2 registers. Oh, we have like 2 versions of add. One of them is with register and register, and one of the immediate, and one of them with just immediate. And there is one with register, register, and register, but there is not this one. R1 comma IP. What's this? So yep, it's just a different encoding of add register. So there's like this and this one. So we did this, and now we need to do this. Let's do it. All right, assembler.ts. So we have oh, we even knew that we had another one to do because we have like a placeholder. We did the first one, we call it adsreg1. So now we need to do adsreg2. Let's just switch sides so it's consistent. Always the tests on the left. Yep. All right, adsreg1. Is it called? No, that one is actually called add, not ads. Okay, let's change this one to adsreg, because there is only one adsreg, and this is adrag. Okay, and then we are taking so add reg R1 and IP should equal, we don't have, I think we got confused by IP in the past. We thought it's PC, but it's actually register number 11 or something like that. So add R1 should equal this. Add R1 IP should equal this. And now let's implement LDRB. Oh, we didn't rename it here. Probably, yep, it renamed the import, not the function. All right, so export function addreg, and let's keep it the order the same as in the datasheet, and that's RDN number, RM number, and the coding is just copying this. Let's see what is this DN. 0B, and that's shifted by 1, 2, 3, 4 by 8, and then we have this DN. What is DN? RDN. Oh, I guess DN is just. Ooh, wow. There is some logic here that we'll need to take care of. Okay. Yeah, but basically DN is just the highest bit of RDN. So we need to, I think we had something like that in the past, but who knows where we had to break like the RDN. Yep. Where we had to break it like into two parts, but I don't remember really where. So let's just redo it. It will probably take less time than finding where we did it before. So yeah, we need to take the RDN, take the highest bit, so that's this bit, and we need to shift it here. So we need to shift this here. So that's shift by 4, and then RM shifted by 3, and then RDN just take the lower bits, and let's also take here just the 4 lower bits. All right. And let's add this import. All right, and it's not happy because we haven't defined the IP. And what's IP? I don't remember. What's the IP? Maybe we have it defined here, or maybe in the spec file. No, that should be LSRG. Renamed it. What did they just do? Yep. Okay. Fix that one. So Google ARM register IP number. Yeah, cool. Nekati says that in the future is planning to run this sim to emulate NES. I would love to see that. Yeah, R12 is IP. And this one also says that R12 is IP, so I guess 2 must be true. And this is green, I guess, or maybe not. Let's see. It's almost green. Why doesn't it assemble it correctly? So R1 and IP, RDN, RM, and shift this. So this one, and in this case, RDN is 12, I guess. No, RDN is like R1, so it should be 1. RDN, yep, it's 1. So what did we get here? Let's print it in. Oh, it should equal hexadecimal, and now it's green. Perfect. I keep making those stupid mistakes today. Don't know why, but forgot this 0x here. Okay, we have the assembler, and now let's just implement the test case, which may require some so we may need to understand some of the spatial cases and account for them as well. But let's start with add reg, and let's add let's do it like before. So adding R1, we want to add IP and define a constant for IP here as well, is 12. So import the function, right? So adding R1, so we can say that IP. Oh, nice. We can check it with the, no, I don't want to check the flex here. So let's add 66 to 44. What's the result? I think it's 110, right? And obviously we don't have it implemented yet. It's not negative, it's not 0, there isn't a carry, and there isn't a negative overflow. We update all the flags, yep. Okay, so but there are a few like interesting cases here. First of all, we need to account for the case if like yep. So if the destination register is 15, like if we are writing to PC, then the flags are not updated. And then what does ALU write PC does? ALU write PC. It doesn't seem like ALU write PC. Branch write PC address, and what does this do? Yeah, it just sets the lowest bit to 0, and then it goes there, I guess. Branch 2, yeah, PC equals address. So let's do this test case. So in case we are adding, let's say add as PC, we are adding there 3, for instance. Oh, that was like R1 IP. So in case the target destination register is like, let's say we are adding R8 to it, and then R8 is like 3. Or actually, let's make it more interesting. No, we don't need to test that. It doesn't update the flags. We can assume it doesn't. All right, so we expect the PC after this instruction to equal. So that was ADD register. Yep. So if both of them are 15, it's unpredictable. Result is adding, the shift is probably 0 shift like always, yep. So basically adding with carry, RN and shifted. So adding this and this. So yeah, so this is interesting. So this is the value of PC before the instruction, but we are adding there 4 because when we are reading, we had this in the past, when we are reading from PC, we always assume it's, I can find it in the datasheet, but we have seen that it's always like treating it as PC plus 4, plus we have here, let's make it 9. we have here 9, so ideally that should, or no, let's make it 11 hexa. So ideally that should have been 15 hexa, because that's 4 plus 11, but we clear the lowest bit, so that should be 14 hexa. So and of course we need to add PC with R8. Yep. All right, so that's this test case for adding PC, and it's not adds, it's just add in this case. And I think there is another interesting case here. If this or this, then see add SP plus register. Like if we are adding to SP, then all right. Let's take a look there if it does anything interesting in SP plus register. Oh, I think there could be this is probably just like the same instruction. I guess the prefix here is the same. So that was 1100. And that was 1101. So let's see, that was 1100. Yes, it's the same encoding, but probably in this case we already implemented that. I guess it doesn't. That was SP plus register. So in this case, well, why? Oh, right. Yeah. So in this case, it just doesn't update the flex. But anyway, we implement this case as a different case. So we just need to make sure it comes SP plus, or we haven't done SP plus register. No, we haven't. So we need to make sure that if it's like SP plus register, then we don't update the flex, if I'm getting that correct. So there isn't anything special here. Like in this case, D is always 13, but they feel that it's necessary to check if D equals 15, even though D is always 13. But I guess the only difference is that the treatment is pretty similar to adding to PC. It doesn't update the flex, but let's make a test case for that as well, just to make sure that we cover that case as well. SPR8 whatever, and not update the flex. So let's say that SP is, let's say, actually it could be 100 hexa, or let's make a value that makes sense. This value, and then we are adding 11, whatever. So we expect SP to equal this plus 11. And now let's do something with it. Let's for instance set 0 to true, and the result is obviously not 0, but we expect it not to update assert it didn't update the flex. Cool. So that would probably account, oh, we need to add it to SP, and we think SP is 13, I think. Let's double check. SP is 13, yep. All right, so okay, let's implement this instruction. One instruction, 3 test cases. So that was add register. So add register. And how is the decoding going? Add register. So add register, that should be the prefix. and then we have like 8 bits, so shift by 8. All right, and then we have so this should be 7 bits, right? RM, and shifted by 3. No, it should be shifted by 3, and we should take 4 bits, so RM, and then RDN is opcode and this, but we also need to take the high bit. So also like opcode, and this bit is like 80, and we need to shift it by 4 just to move it from here to here, so it will be the high bit of RDN. By the way, Nekarian, I'm still thinking about your question, why not? And I have no reason why not to to use this sim to emulate NES. So do it, please. Anyway, so left value is, does it matter? I don't think it does. RDN, and then result is left value true. But wait a second, there is like this special case if D, and D is RDN. So if this one RDN equals 15, then it's like this is plus 2, and we are doing plus 2 because at the beginning we already added 2, otherwise it's just reading from the register. So this is like the special case for PC, and then RDN is result, and this test case passes. Now we have to fix the flag. So if RDN, we only do it if RDN is not certain, so it's not SP, and RDN is not PC. Let's maybe reg SP, give them meaningful names, so this code is a bit more readable. So instead of 13, if it's not SP and PC, and here if it is PC and not OR. All right. Okay, so this one also passes, the one with the SP, and now this one doesn't pass because if it's so if the RDN is reg PC, we should also like clear the lowest bit of result. So if it's reg PC, it should be result, and that would clear the lowest bit. Are we happy? Not yet. Expected this, received, oh, and not this. All right, this is also happy. So hopefully we understood all the edge cases correctly and we implemented them. And now we have finally finished fulfilling our promise from last week to add all of those instructions. And let's run it. And I expect to have the same result where, yeah, we panic, and now we need to figure out why we panic and fix that as well. But now it's very less likely to do with unimplemented instructions. We still have a few that we haven't implemented, like DMB. We said, you know what, let's just do it. It's like I think just to reduce the noise. This is like a very specific opcode. So yep. DMB, and there is like operation, which is like everything always like 1 1 1 1 1. So basically we can just add a if case for that. So we know that this should be the encoding. No, you know what, let's not do it right now. Or no, I will do it. I just don't like this noise that we are seeing here. Let's see what's this instruction though. CPSAD, what's CPSAD? Priority mask. probably primask PM. So I have no idea what these are doing. Change processor state. All right, I think we can ignore it for now as well. Anyway, yeah, seems like other than those instructions and then a few instructions in, well, why do we execute from the memory? Where did we get into that? Here we had, no, this is the first instruction before jumping to the, no, this one. Finally, before jumping to executing from the RAM. Let's see what happened there. Mutex try enter veneer. Okay. Okay, so mutex try enter. All right, not sure what's going on here, but this might be an implementation. Okay, anyway, it runs something from the RAM, but then it goes back, so I think we are fine with that. We don't need to debug that right now. Let's go back, and it goes back to the RAM. I'm just wondering, you know what, let's do something like that. Whenever we have instruction that we don't recognize, let's just print the instruction so we can disassemble it and see if it's important. So that's in run link, and then no, it's like in the RP2040, and then let's just print it. Opcode to string 16, and then if we have another opcode, just print that in parentheses, because usually it's just the opcode for the next instruction, so we don't really care about that, but sometimes we do. All right, let's print this. Okay, so yeah, now we can see like those missing instructions, what they are, like what's that? Where is the disassembler that we found last time? So yep. This is ARM, thumb, default. What's that? Do we need to change? Yeah, we need to change the order of bytes, I guess, but how comes it's out of bounds? Oh, default? ARM thumb. Are we forcing thumb? Yes. Let's just reload this, maybe. Oh. Perfect, server error. Yep. So this one is broken. Anyway, yeah, let's go back to figuring out what's wrong with panic, and we'll look at those missing instructions in the RAM later. They might not be relevant at the moment. So yeah. This is where it's starting to, thanks Nikati, this is where it starts to get interesting, I guess, where we actually try to figure out what is going on here. All right, so we had like this panic, and it started rep puts, that was called from the panic, but where did the panic start? Panic started here, and it was called from here, hard assertion, and that was called from this one, IRQ set exclusive handler. So yep, something in the exclusive handler, it expected the value and it wasn't there, and we are reading this value in this location. What's this? This is loading. Let's open it side by side with the source code. So That was IRQ set exclusive handler. I think that was the one. Okay. All right. So why do I have this? Okay. So I guess this is probably doing something like this one, like creating the get vtable handler with num. I guess num is, so the first argument, I guess it's, where do we get a value of R4 from R0? Adding, so I guess name is like passed in R0, and then we are adding 16 to it, and then shifting something. Yes, that's probably this comparison. So we are comparing R3. So R3 is like this, probably this value of current. We are first comparing it with this R2, and then we are comparing it with R5, which is our first argument, which is handler. So that makes sense. So basically, that's what the code is doing. So I'm pretty certain that this LDR, yeah, so this is probably like the value it expects here in R2, which is loaded from here. So it expects this value. And we know that we read a value that seems, oh, wait a second. Yeah, that's, okay, so this read is like this LDR, this is the second LDR, but we are interested in the result of the first LDR. It should be equal to this one, right? Because if not, we are hard assertion failure, but it's not. So what happens here? We don't have a debug print here, but why is that? LDR. Where do we print this reading from? Oh, it's only in a specific LDR literal. We left it to debug something in the past. So let's just copy it to, yeah. Let's copy it to LDR register, and then we'll have something similar in the output for, yeah. So yeah, so we are reading from this address, and we get FFFF, and this seems to be 1, 2, 3, 4, 5. Huh? I think there are too many. Interesting. It's more than, like, there are 8, right? 1, 2, yep. So it's reading from an address that shouldn't exist. Yeah. Okay, interesting. What is this? Something either is totally wrong. Like this shouldn't be possible. Like first of all, this is a bug. Like we should always, maybe we are doing it here, but this result shouldn't be more than like 32 bytes in any case. But for some reason, like from 32 bits, for some reason, in this case, the result was more than 32 bits. And I guess I know what happened here. So we are reading from this undefined value. We probably read something. Maybe this one. No, this is the same. But we probably at some point read something that returned this, and then we added this like yeah, we added this other number, so we have like adding R4 to it. So probably we already like hit a problem here. So let's see what it's doing. It's like loading this value into R3. So it's reading from this memory address. So basically, I guess it's reading from there. It's getting all Fs because that's the default value that we return for addresses. We have no idea what's there. And then it's the next thing it's doing, it's adding 8 to it and reading from F plus 8, which is just throws it off. So first of all, there is like a subtle bug here. We should always make sure that the addresses are like 32 bits and nothing more. I think that's an easier way to convert it into 32 bits. Just or it with 0. Tells JavaScript we need it to be 32 bits and nothing more. Let's try that. Oh wow. Or where did that happen? 4B. Yep. At least it so instead of 1004B, it read from the right location. But then why did we have to string of undefined? Reading from this location returned undefined. Interesting. So this location is, I guess, that was, where were we? 4B. Yeah, this is like not 4-byte aligned, and I guess that's why. So this is like our nice way to so I guess what happened here, we are reading from this address, and it's the read is not 32-bit aligned. So this value is actually let's do this. So it's 4B divided by 4. And since this does not really divide, we get this value, and this is not a valid index into boot ROM, so we get undefined. So this behavior is totally fine. We should probably raise a hard fault here, but we don't care about that now. We raised another kind of hard fault, and that's only because we are trying to actually no. This is not good, because if we really encounter that in code in real life situation like we have now, and we don't have those debug prints, then we'll have a problem, because we'll put undefined into this value and then it will get carried away. And let's just if address, let's just make it proper now. So if there is like, if it's not, we no longer assume that. So new error, address is not 32-bit aligned. And at some point we'll get, maybe let's print the address as well. At some point we will read from address to string 16. So at some point we'll probably get to generating the default in the CPU, but for now at least we have like this sort of guard that will make sure that the user knows that, or we know that we got something wrong here, and the error doesn't carry away because we don't just get undefined and put that into register and then things go wrong. Anyway, so the problem is here. We are reading from this value, from this address, and it shouldn't be all Fs, but it is. So let's see what's this address. Let's go to the RP datasheet. What's here? Oh, maybe we'll start here. Yep. Ooh, internal registers. Is it documented anywhere? So chegewaras says something, yep. Chegewaras has a good point here. we do need a fake DMP opcode because it's 2 bytes. So we need to skip over the second byte. Otherwise, we always try to execute 2 instructions. So I take that, and let's do that real quick before we go on. So where was that DMB? Git log. Yep. So good point. I totally agree with that. Okay, let's do the assembler. So I hate those like 2 bytes instructions because I'm not sure how we should break them. Anyway, assembler. We'll try to figure out how we did it with BL, and then it will be fine. So it should DMB. Okay, let's add it here. It should correctly encode DMP, and it shouldn't be N actually. DMP DMBSY instruction. So to our past self, no, maybe not. We are doing it. We have a good reason to do it, just because it's 4-byte opcode and not 2. So expect opcode DMB SY. Oh, we don't even need a function for that, but let's do it just for, it's like a constant. I'm just not sure if, I guess it should be like this. Maybe we can compare it to what we did with this BX or BL, sorry, BL. So BL, oh, but yep. We won't be able to find that in the code because that's like relative BL. So that's not very helpful. DMBSY. Okay, we'll just so yeah, so what I'm going to do, I'm going to ditch the test case for now. We'll just do something like this. So we don't really care about decoding this instruction, so just make sure DMBSY. We'll just try both cases. So it's like constant value, so there are only 2 options. If that should be else. If opcode is this one, and opcode 2 is this one, just PC plus equal to, right? Skip. That should be 0x. Yeah, now let's see. Where did we have those DMBs? Like here. Do we have it in the output? Yep. Yeah, this is easy. We now see so this is the first one and this is the second one. Yep. Yeah, that's good. So let's just console log it so we see that we are doing the right thing. So we basically expect this one now to to decode correctly, and then we skip right to the next instruction. So yeah, so that could have done some damage if we didn't do it, because as chegewaras says, and I think I don't know if we have this like in the undo buffer. Yes, we do. You see, before we did this, it says I don't recognize this instruction, and it skipped it, but then it executed some random instruction, basically this one. Let's see if this disassembler is working. You know what, never mind. It just executed some other instructions, whatever this decodes to. I'm not sure what this is. And you know what, we can test this, like see which instruction this is. If we just go to the, where was that? To the test code, RP2040 spec. I always the test code here. Okay, if we go to the text code and just like duplicate some random test case and put this value in the opcode. So, and focus on that, and then go to the RP2040, we can see which instruction is executed, and then figure out what this second byte decoded to. That was the second one, or the first one? No, that was, yeah, that was the second byte. Oh yeah. So yeah, so before we like implemented those this DMBSY, this opcode was encountered, it was interpreted as LDRH, which shouldn't be there. So it probably has destroyed the value of one of the registers, because it just loaded some random data from the memory into a register, and that could have been really tricky to raise down later. So I'm really thankful to you, chegewaras, though, for just making me aware of this. That has probably saved us a bunch of time in the future. So thank you so much. And now, after fixing that, that was a very valid point. We should no longer see this. Oh, let's just reopen this. Output, go away. Go away. There is probably another copy of it here. Yep. Okay, let's reopen it. Yep. And now it just skip 4 bytes and doesn't do that anymore, and we don't have to worry about that. But now we still have this problem where we are reading from this. Where were we? Oh yeah, IRQ set exclusive handler. We were reading from, I think we have it here as well, from this address, which is some internal that was PPR base. Yep. And I'm pretty negative that we are going to find anything about this in this data sheet, but maybe in the Cortex there is something about that. System control block. Okay, interesting. So what's inside the system control block? CPU ID base register. That's what we are reading from, right? E00 ED00. And that's implementation defined. That's the reason value. I'm not sure. It should equal. Wait a second. Let's see what this does. It will probably be clearer when we see. It calls get vtable, and then it adds 16, and I think we have seen this 16. I remember we have seen this 16 inside this IRQ set exclusive handler. Where is that? 16, 16, 16, 16. Yeah, this 16. So adding this 16 to num, which is the first parameter of IRQ set exclusive handler, and then we call get vtable, which is probably where is that defined? SCBHW VTOR. What is SCBHW? PPB base M plus CPU ID offset. So that's the right thing. So we are reading from the there is like CPU ID VTOR. So yeah, it's like it has some bits, but I don't think we are looking at the right thing. I don't think it's reading from the CPU ID. Like wait a second, STBHW, so this one, and VTOR, it's like reading from here. And what's it, VTOR? So that's here, vector table offset register. So we are reading from the vector table offset register. And if I'm not mistaken, this was written by boot stage 2. But we should be reading from here, not from here. Why are we reading? Oh, yeah. This is like, yeah, I guess this is, this happens here. So IRQ get vtable handler. So we are reading this value and then we are adding yeah, and then we are adding 8 to it here. So we should be reading from this plus 8, and that's here. And so we are probably not printing that read because this is done with LDRR3. It should be printing that. Why don't we have this memory read print? We have LDR. I think that should. Is that a different instruction? It seems to be like the same one as this one, the same variant. You obviously implemented it, otherwise we would have gotten an error. Interesting. Anyway, so it should be reading from this address, and it's getting zeros because we haven't implemented that. Let's try to just, implement the read hook for that address. So let's say let's say that, let's do it in the RP2040 class. Read hooks dot set. All right, so at this offset, let's just console log we read from VTOR, from Victor. Let's call it Victor, just to make things a bit more fun. Otherwise, it would get boring. Okay, and output. Let's take another look at the output. Let's open them side by side. Output. Yep. So we read from Victor, and now when we return a different value, we can see that the result is also different. How come we got a negative address? Yeah, I think the trick that we did, where was that? So when we had like this address, so I think this is like, where was that? That was in LDR. Yep, I think this one is actually yeah, I think if I'm not mistaken, this one is actually making it signed integer, and then if we use this one, it will get unsigned, which is what we want in this case. Yep, it did work better. We still got into that panic, but now we are not reading from a negative address, which is bad. So let's also give this same treatment. Maybe we should do it inside read uint32 instead of like everything that calls it. So address, just make sure it's like round to 32 bits unsigned. All right, cool. So yep, so we have those fancy reads now, and we can see all of them now. They were probably negative before, I don't know. Anyway, we still get into panic, which makes sense, but now we have this Victor we are reading from, and then after reading from Victor, now we are reading from this address, whatever. Yeah, so we just returned like some arbitrary value for this VTOR, and that shouldn't be what we return. There is like I think in the beginning this vector table is initialized to 0, something like that, and then the reset value. And then I think at some point in the boot stage 2, this is overridden, but we have probably not implemented that, and that's one of the problems. So let's take a look at the boot stage 2. I think it was like one of those includes yep, I think this one, M0 plus VTOR offset. I think it's actually writing to this same place where we are reading from right now. Let's create a right hook there and see if we get anything. So if somebody is using that writing there. So we write to Victor. Let's have a VTOR is 0, and let's just, you know, VTOR equals new value. So whenever we write, we just write it into VTOR, and then when we read, we return this value. Okay, new value is number. It's not happy. Oh, this should be right hooks. Thanks TypeScript for being helpful again. All right, so okay, let's start it again and see what happens. First of all, I think we are still, Yep, we are still in this panic. So let's see if we are actually, yeah, we write to Victor, nice. So somebody wrote to Victor, and then we have an unimplemented instruction. I think, what is that instruction? It might be throwing us off as well. What's there? I think that's something in the bootloader, probably MSR. I don't think we implemented MSR. I think it's like that, doing something with the stack register. Let's first of all, yeah, another 16-bit instruction. So yeah, I think it should deserve the same treatment as DMB, because otherwise we just execute something and we have no idea what we are executing. But before we do that, we now write to Victor and we read from it multiple times. And now after, oh, interesting, we're reading from this Victor somewhere in this bootrom code. We write it again, we read from it again. And what's this? Not implemented instruction. MRS. So MRS. Another 16-bit instruction. Yeah, we should just ignore those. MRS. Or maybe we shouldn't ignore those, but we should definitely make sure they don't execute, like this doesn't execute, because this may throw us totally off. And this might be the reason why we are still getting into this panic. So let's just decode those correctly. So we have this MRS and it has RD and sysm. And then there is MSR, which has RN and sysn. Let's do them. Let's create them. Cool. So MRS and MSR. Where are you? MRS and MSR. You will be in our assembler spec file. What did I do here? Why did I do it like that? All right. So let's correctly encode MRS, MSR, MRS. So MRS should be this one. I think this should be like that. Yeah, it makes sense to me that it should be this way. MRS. Now I need to figure what's primask, but we'll figure it in a moment. So MRS R6 and primask. And then there is like MSR, right? Which is just the opposite. MSR primask R6, so MSR prime, probably something with masking interrupts. Okay, so primasks should be equal this, but I'm actually not sure if this is like the right order of bytes or I got it reversed, because yeah, I think this one should be the higher one. Okay, this may make sense, may not. We'll know it in a few minutes when we get to testing this. But first of all, let's check what's the value of this primask. What is this primask? Yep, but what's the index of that? Primask. Mm-hmm. 16, right? It seems to be 16. Yeah, maybe we can just, there is a way to read the flex register. Interesting. Anyway, let's just copy all of those constants so we have them. Or no, let's start with primask for now, for the test case. So primask should equal 16, right? That was 16, yep. Now we can encode MRS and MSR and check if MRS, so MRS is like assembler. So MRS is getting RD with spec reg. MRS RD with spec spatial register. And then the encoding is, I guess this is the high byte and this is the low byte, or maybe not. But why doesn't it let me copy this? Isn't there a friendly way to copy it? Okay, I will just remember there is like a 1 there. So the highest byte, I guess, is just like this. Oh, and there was another one here. Yeah, 4 ones, right? 4 ones, yes. And go away parentheses. Right, so this should be 16, so this is 6, 5 and 5, good. So shifted by 16, I hope, or maybe not, we'll figure it out soon. And then we have like the low one, which is this one shifted by 12. Shifted by 12, and then RD, and that's 4 bits, shifted by 8, and spec reg is just a lower byte. All right, let's see if we did it right, or we need to. That was MRS. Okay. Probably the byte should be reversed, so this should be probably not shifted at all, and this should be shifted by 28, and then this one should be shifted by, oh wait a second, maybe this was correct, but this should have been bitwise ORed and not ended. Oh, it's still not happy. Probably. Let's just make sure it's signed, because it seems like obviously this is a negative value if we look at it as unsigned, but yeah, it's still not correct. So I guess, yep, this should be 8. So yeah, so we should reverse those bytes. So this should be shifted by 28, and this should be shifted by 24, and this should be shifted by 16, and this shouldn't be shifted at all. All right. Okay, so now this passes. Maybe let's just, for the good measures, make sure it's always positive. What have I done here? Why did I apply this twice? Yeah. Everything. Yeah. Why does... Oh, it just added another set of parentheses. Some strange formatting. Anyway, so we got MRS. Now let's do MSR, export function, opcode MSR, and MSR takes no, they come together. So this one, this is like, we know that this is probably the high byte. Spec reg and RN. RN is number as well, and then we return. So the high byte is like this. Why do they have all those values in parentheses? It doesn't make our life easier. Right, so this one shifted by 8, and then there is like spec reg, and then there is the high byte. Oh, we said this one goes high, right? Yep. So this is shifted by 24, this is shifted by 16, and then we have like this happy thing, and finally our RN. So 1 1 1 1 1. Okay. And this will be shifted by 4, and then we have RN, and F. Okay, let's import it, and it doesn't pass. It fails, maybe for the very same reason as the other one. Let's just make it positive. Still fails. Okay, so what did we do incorrectly? Seems very close, so like the expected and the received number, they seem very similar, so it must be something super. Oh yeah, bitwise OR. I did it, but it's still not happy. I don't need those parentheses anymore. Okay. Still not happy though. So 1 0 0 0 0 1 0. Still very close numbers. Oh, wait a second. This is 1 1 1 1, and this is, yeah, I needed another one here. Now it's green. Perfect. Another. It didn't let me copy the one, like it didn't here, so that was the problem. Okay, so we got the opcodes. Now we can do test cases real quick. So actually, thinking of it, we don't really need the test cases. We just need to skip them right now. Or maybe we should implement them. Yeah, let's do that. Like it's for now. Let's just so it's 256. This is there's like anything that explains what? Yeah, so 6m should be one of those values. So we can just you know, set up an array with this number of entries, and then yeah, and then for now, I mean, we should probably like do this properly, like copy the flex register and whatever. But for now, let's just print a debug that we need to do it and not do it. So let's do the decoding and not create a test case for now. But we have the assembler for whenever we want to do. So there is like MSR and MRS. So MRS is, so if this is oh, wait a second, this is the first byte, the one with the F, so this should be the first byte. So maybe we did encoding wrong, not sure about that. Anyway, the decoding has to be correct right now. So let's just copy it from the encoding. Instead of, so the first byte should just be equal to this, right? If opcode equals to this and opcode to we want the highest 12 bytes, so we'll shift it. I mean, we want to skip the lowest 12 bits, should equal 0b, that's 1000. So and same goes for MSR. So with MSR, I think the decoding is a bit more complicated because we only want to check fewer bits. So if opcode shifted by 4 is this, and opcode 2 shifted by 8 is, I think we had this here, this. We don't need this anymore. Is this, then this is MSR. Okay, let's run this and see if we get MRS and MSR where we should. That's here, 3E, MRS. But then we should also do what we did with the reason why we did this, and what we did with this DMB, this.pc plus equals to skip the second opcode, not to execute it as an instruction. All right, let's run it again. And I'm not optimistic this will get us any further, but yeah, we are still in panic in this annoying loop, but at least now we know we won't be beaten by this in the future. Anyway, I think we have done enough for one day, and I think other than this like break instruction, there might be only like very few instructions that we still haven't implemented. Like, what's that one? Oh, that's in the memory. We can't easily, we can view the opcode, but let's take a look at this one. So, yep, probably like, this is probably important. stdio put string, yep. So let's commit and take a note to implement it next time, but it seems like we are almost there in terms of implementing the instructions. So this one and this one and this one, not for now. It's all like the debug prints we added last time. We hopefully won't need them, but we definitely don't need them in the repository for now. All right, so yeah, feature RP2040, almost all instructions. What did we implement today? So we added add register, and we have LDRB register, LDRH register, LDR register. We did a lot today. LDRSB, LDRSH, and then we did all those. Oh, LSLS register, and then we add STRB, STR. We only had STR before. Now we did all the register, STRH, STRH register, and I think we didn't have STR register as well. So yeah, and we also implemented VTOR. Right? We did this, which maybe we should, instead of using this magic constant, we should give it a good name, like that was how did we call that? PPB base? No, that was like something like CPU ID base. How did we name that in the SCB, system control block? Okay. Const system control block is here. And then we had this like VTOR, which is this plus 8. Maybe there is a better name than offset VTOR, but it should do. It should be good enough for now. We can always rename it. At least it's not a magic number, and we know what it means. All right, so we did that as well. Cool. So let's add that one. That's single change as well. ed08. Cool. All right. So yeah, we are going deeper down the rabbit hole. I hope that next week, we wanted to just next time. So we add this missing add instruction. Let's do a really quick search if we have another not implemented yet. So this one is, I think, 442. Yeah, I think CPSAD. Maybe we should just let's take a look at this next time. Maybe we should just didn't want to commit yet. Maybe we should just ignore it. It's just single opcode, so just 2 bytes, so it shouldn't interfere with the decoding of the next instruction, but it's still noise. Let's see what's here. LSRS. Oh, we are still missing one variation of LSRS with 2 registers. We'll do that next time. What's here? CPSAD. So that's 44908. What's here? Another CPSAD. Different encoding though. And this one is another CPSAD. Yeah, it definitely creates a lot of noise, this CPSAD. And we have, I think we already have this on the list, right? And then this is memory. Oh, we are pretty close, I think, to, oh, why don't we have this LDR? Are we still missing a variation of LDR? Is that so? Well, that's what it says. And then this one is the add, the same variation of add. And what's that? STR. So we are also missing this variation of STR. I wonder how we missed that today. I thought we finished with the LDR and SDR. So we may have some interesting bug in the decoding, or we may have missed something if those are not decoded correctly. Okay, let's see if we have anything else left. Yeah, another ADD. Okay, we have a lot of them like down here, but I think they are pretty much repetitive, and these are like in the RAM. And I think this will be the last one we'll look at today. They probably pretty much repeating, yeah, this add. So yeah, so we have a bunch of missing instruction to look at for the next time. These are actually not interesting anymore. So we were at 17. Yeah, this is memory. Yeah, and this is also the already those breakpoint instructions. So you know what? Let's just to reduce the noise, let's just decode it and do a debug print next time. So we have 6 instructions that we know for sure that are missing. And once we figure out those missing instructions, I'm pretty positive that those RAM instructions will disappear, unless we are, jumping to some random memory area and executing some random code. I'm pretty positive it's not the case, because that code that runs from RAM eventually returns. So it's probably legit code. Not sure why it happens, but it's probably something that should happen. But once we have those instructions, then we will be pretty certain that the code does what it should do, or we have bugs. Like, I think those 2 are bugs, but that's for next week. So let's commit. Okay, next time. Okay, let's commit and push that, and let's see. See you next Tuesday when we will hopefully try to finish those missing 6 instructions, and then we'll probably keep tackling those reads from registers here in this whatever it was that led us to panic or to hard assertion failure, and we'll probably have to tackle a few more I/O registers that are being read throughout the initialization, until at some point, maybe next week, maybe not, we'll have this happy moment where it suddenly works and we're like, wow, finally that happened. And then we'll look into MicroPython or whatever you want, PPI, whatever you want. So anyway, until the next time, have a great rest of the week and see you next Tuesday. So bye bye.